Webinar after our semester of hiatus. I'm Michelle, I'm a new organizer. So today we're excited to have Giancarlo Travaglini speaking on irregularities of distribution and convex planar sets. So you can take it away whenever you're ready.
Okay, so I start now.
Yes.
Okay, first, thank you very much. I'd like to be part of this webinar, and I hope we'll have other possibilities to meet and talk and discuss. Okay, so let's start. According to mathematical reviews, the term irregularity of distribution was invented by Roth in 1954. It never appeared in a mathematical paper before. And we are referring to a pretty famous paper of Klaus Roth, which started from a conjecture of van der Corput, which we shall talk again about in a moment. Perhaps it is interesting to know that Roth considered this paper to be his best work, which you know what Roth did in mathematics, so is a quite interesting fact. The reason is that Roth said that this paper started a new field, and most of this talk will be an attempt to describe what can be considered a new field in this sense. We shall go back to the conjecture of van der Corput, which you may read in the picture, but we shall discuss it in a moment. First, it may be interesting to take 2 steps back. The first step goes back to 1884, Kronecker. Kronecker proved the general approximation theorem, which in one variable takes this form. Take any irrational number, then the set of the fractional parts of the arithmetic progression alpha to alpha 3 alpha is dense in 0, 1. This result can be translated into several variables. We just have to replace the irrational number alpha, not with a pair of irrational number, but with a pair of irrational number with the following property. Take an integer combination of this number and suppose that the sum is an integer. Then all the coefficients must be 0. So square root of 2, square root of 3 is okay. Square root of 2, 1 less square root of 2 is a pair of irrational numbers, but does not work. Kronecker's theorem says that the sequence J alpha is dense in TD, where T is the torus. Please feel free to stop me when, because I don't have an immediate feeling of whether it's clear or not what I'm saying. The next step came with the study of uniformly distributed sequences, which goes back to the 10th of the 20th century, and is due to Hermann Weyl, basically in his mathematician Allen paper. Weyl's work was primarily intended as a refinement of Kronecker's theorem, and therefore, in its initial stage, Weyl's theory was deeply rooted in Diophantine approximation. Let's write a definition. Take an infinite sequence taking value in the unit interval 0, 1. we say that the sequence is uniformly distributed if for every interval a, b in 0, 1, the limit of the ratio between the number of points in the interval a, b with index less than n, capital N, over capital N is equal to the length of the interval. This means that take n large, then take an interval, say, of length 1 over 4. Then about 25% of the points must fall in this interval. So every interval has asymptotically its proper share of points. Uniformly distributed sequences are obviously dense, but the converse fails. Basically, density is a property of the set. Uniform distribution is a property of the sequence. If we have a sequence which is uniformly distributed in 0, 1 in the sense that its fractional parts are uniformly distributed in 0, 1, we say that the sequence is uniformly distributed modulus 1, or uniformly distributed in the torus. It's not difficult to extend this definition to several variables. Just replace a generic interval with a parallelepiped or a d-dimensional interval, and the definition is exactly the same. Weil proved that the above sequence J alpha is uniformly distributed, and this was a direct consequence of the celebrated Weil's criterion. Weil's criterion says this: let Tj be a sequence taking values in the d-dimensional torus, in the d-dimensional cube. Then the following are equivalent. First, T of j is uniformly distributed. Second, for every Riemann integrable function, the value of the integral can be taken as the limit of the Riemann sums associated to the sequence Tj. Third, for every non-zero vector k in Zd with integer coefficients, the average of the exponentials e to the 2 pi I k Tj is equal to 0. The equivalence between 1 and 2 is quite natural, because if we take the characteristic function of an interval, then we have a particular case of a Riemann integrable function. On the other hand, characteristic function of intervals are the building block for Riemann integrable functions. In order to see that the second property implies the third one, observe that the last sum, the sum of where the exponential appears, is a Riemann sum, is the Riemann sum of this integral, which we know to be 0, when k is different from 0. The converse is the less easy part, and it depends on a completeness argument. The second property is, of course, important in numerical integration, especially in many variables, at least as a starting point. The third term, which is what is more widely known as the Weil criterion, is one of the classical applications of Fourier series. For example, see the book by Stein and Shakarsky, or the Fourier analysis book by Montgomery. Observe that this condition, the one we pointed out in a moment ago, is quite strong. Assume we are in the one-dimensional case, so that the exponentials are points in the unit circle. If we want this sum to be small, then the endpoint must be well distributed, whatever it means. But then the same must happen for twice this point, 3 times this point, and so on. So that it is clear that it is not obvious how to keep all these sums small. So it is not obvious how to build uniformly distributed sequences. Now we can prove Weil's refinement of Kronecker's theorem. By Weil criterion, it is enough to prove that for every choice of a non-zero integer vector, we have this limit equal to 0. And this is quite easy because the sum in the limit is a geometric sum. We compute it explicitly, and we see that this average goes to 0 because of our choice of alpha 1, alpha 2, alpha d, the condition we said before. In one variable, it is enough to say that alpha is irrational. The definition of uniform distribution consists of a limit. The definition of discrepancy is its quantitative counterpart. For example, we may wish to find a finite set in such a way that its discrepancy is small. Remember, discrepancy means to compare a continuous object, the area of a set, of a reasonably simple set, with a sampling. For example, it's a Riemann sum. So basically is a comparison between continuous and discrete. The so-called van der Corput sequence represents a best possible way to choose an infinite sequence in the unit interval with small discrepancy. It's quite natural. I believe that if we don't know it and we are said to put a sequence of points in the most even way we may guess in the unit interval, we should arrive to this sequence. So where do we put the first term? 1/2, and then 1/4, 3/4, and then 1/8, 5/8, 3/8, 3/8. So this is a quite natural way, and it has a pretty neat definition, which is which is as follows: take an index j and write it in base 2. Then the point t of j is defined as this this term in base 2. Take j equal to ak 2 to the k, then t of j is ak 2 to the minus k minus 1. The key point is that this sequence has small discrepancy when n is a power of 2. For example, when we arrive, when we end the denominator, 1/2, 1/4, 3/4, they are pretty well distributed. Then when we end the denominator 8, again, they are pretty well distributed, and so on, but not in between. It can be proved that this sequence has the discrepancy of this sequence is not as small as one should expect. On the other hand, it's not very large. It is essentially, it is bounded from above by a logarithm. The reason is that take any n any positive integer n, and write it as a sum of powers of 2. The powers of 2, like 1 over 4, 3 over 4, 1 over 8, 5 over 8, and so on. When you add the power of 2, the distribution is pretty good. Each power of 2 is well distributed. So you have a distribution of points which is a sum of which is the union of a family of blocks. Each one of them has a smallest possible discrepancy. So you only have to count them. And how many power blocks do you build before n? At most log n. That's why the Van der Corpus sequence has a log n upper bound. But this cannot be improved. This is sharp. The same is true for certain Kronecker sequence. For example, you take alpha equals square root of 2, and you take the arithmetic progression, square root of 2, twice square root of 2, 3 times square root of 2 on the torus, on the circle. And again, you get a logarithmic discrepancy. The example of the Van der Corpus sequence suggests that every infinite sequence has an unbounded discrepancy. And this was the conjecture by Van der Corpus, which he stated in the following form. Take an infinite sequence of real number S1, S2, S3. Then, corresponding to any arbitrary large k, there exists a positive integer n and 2 subintervals of equal length, such that the number of terms S1, S2, and so on that lie in one differs from the number that lie in the other one by more than k. In other words, take an infinite sequence, you can find 2 intervals of the same length which has a very different number of points of the sequence inside. And now we are back to Ross' 1944 paper. Ross' paper provided a proof, it was not the first one, of the Van der Corpus conjecture. A peculiarity is that his proof used a planar argument. The original problem was one-dimensional, but Roth studied a two-dimensional problem. And this was the starting point for a sort of geometric point of view. So Roth's theorem is in this form, as this form. Take an integer n and take n points in the unit square. Then the difference, if you take this, the L2 norm over x and y of the difference between the number of points in the rectangle 0x, 0y, less the area, times n, this is large. And this implied Van der Corpus conjecture, the proof of Van der Corpus conjecture. So Ross' argument tests the quality of the sampling points against a family of rectangles. So we have some points in the square, and we check for a whole family of rectangles, moving the right upper vertex. We have a whole family of rectangles, and we compare the number of points and the area of the rectangle. 2 years later, on Mathematica, Davenport proved that Ross' lower bound cannot be improved. Davenport constructed an n-point set coming from a piece of a lattice, and using the Diophantine properties of numbers like square root of 2, he created a situation where you don't meet too many points at the same time. In a sense, imagine you have put the points in the square, and then you move the rectangle. The rectangle moved by parallel sides. The choice of point made by Davenport implied that you don't meet too many points at the same time. What does it mean not to meet too many points? Suppose that you put a point on a grid parallel to the axis. Then you meet a lot of points at the same time. That argument was related to an earlier result of Addy and Littlewood, who considered a triangle, as in this figure, where the slope of the hypotenuse is a badly approximable number. They proved that the number of lattice points is a good approximation of the area of the triangle. So this was the setting for the converse of Ross result. Several years later, Montgomery used Fourier series to prove the following result, which was later proved to be equivalent to Ross' theorem. Take a finite set of n points in the unit square. Then you have this lower bound for the L2 norm over dilation. We take a square 0 lambda square, and translation 0 lambda square plus t. This is quite convenient. It's quite convenient point of view because we have abandoned the rectangles 0x times 0y, and we have a square and it's dilated and translated, which are objects well tailored for a Fourier analytic approach. Wolfgang Schmidt, Joseph Beck, and Hugh Montgomery observed that replacing rectangle with disk gives quite a different lower bound. Take a disk in the unit square, then for every set of n points, the same L2 discrepancy we considered before as a lower bound, which is a power of n. So quite different from the logarithmic estimate, from the sharp logarithmic estimate in Ross' paper. And this is sharp too. It can be proved it is sharp either considering points of a grid or random points in small aligned squares. In the fifth example, the upper bound comes from an old result of Kendall on the shifted version of Gauss circle problem. So we have a quite different situation, a small discrepancy, a small lower bound discrepancy for rectangle, and a much higher lower bound discrepancy for disks. And so it was a quite interesting question to understand why. What does it mean? Are there particular case or boundary cases of something else? In a sense, he started the study of the interplay between discrepancy, which means the quality of the choice of sampling points, and geometry of the sets we are moving in. We are moving inside. Observe that choosing a very large or a very small family of sets makes little sense. It is meaningful to consider family of, say, translated and dilated disk, rectangle, polygons, convex body, and look for finite sequences which yield a small discrepancy for the whole family. So this is the setting we are moving. The basic reference are the book by Beck and Chen, and a book by Jiri Matusek. The term geometric discrepancy started replacing the term irregularity of distribution when the geometric aspect starting to be relevant. In this talk, we present the following results. First, when we have a convex body with C2 boundary, we have the same lower boundary that we have for the case of a disk. This was, we found it reasonably interesting because it is quite common in this problem in Fourier analysis to start with the case of positive curvature. And so it came a bit as a surprise, the fact that positive curvature does not play any role. It's just a matter of regularity of the boundary. Second, if we have a convex body which is piecewise C2 and is not a polygon, then we have another power, n to the 1/5. And moreover, we have a whole range of intermediate sharp results between n to the 1/5 and n to the 1/4. So these are the results we try to give an idea of. Our argument depends on Montgomery's approach. Montgomery's approach for the disk discrepancy, and I'm trying to outline it. Montgomery's argument. Take a disk, so I'm describing Montgomery's disk theorem. Take a disk, take n point in the unit square. Take a dilation lambda and consider what we call the discrepancy function, which we see primarily as a function of t, of the translation t. So we compare the number of points in the dilated disk, dilated and translated disk with the area. It is not very difficult to write the Fourier series of the discrepancy function, which is as follows. This is the Fourier series of the discrepancy function. So that then we can use Parseval identity and write the L2 norms in terms of Fourier coefficients. Now, the difficult part is the term in the middle, this exponentials, this sum of exponentials. In general, it is difficult to say something about such a sum, but Montgomery proved a useful variation of a null result by Cassels, which runs as follows, and which should be called lemma of Cassels-Montgomery. I state it in a particular case. Take a positive integer n and take a square of side, say, about square root of n. Then the sum of the exponentials e to the 2 pi I mtj square, when m is in the above square, is larger than n square. So let's go back to this term. We have to bound this. In order to bound this, we take several, we don't bound it term by a term, but we take several terms together. and we have this lower bound. Then we have to take care of the other term. The other term is the term on the right here, which involves the Fourier transform of the characteristic function of B. You have to add estimates for the decay of this Fourier transform. And then in this way, one can get, without too much effort, the following result, which is the result of Schmidt-Beck-Montgomery, which I write again. So take a disk, then the L2 norm of the discrepancy, the square of the L2 norm of the discrepancy is larger than n to the 1 over 2. There has been some extension of this result. The result of Roth has been extended to convex polygon. The result of Schmidt-Beck-Montgomery has been extended to convex body with smooth boundary having positive curvature. We try to get a better understanding, and the first result I try to describe is the one I mentioned before. Positive curvature apparently does not play a role. So let's C be a convex body with C2 boundary. Then the discrepancy, the L2 norm, the square of the L2 norm of the discrepancy is larger than n to the 1 over 2. The case of a disk show that the above inequality cannot be improved. The proof depends on a close relation between the Fourier transform of the characteristic function of C and certain chords between points in the boundary of delta C, in the boundary delta C. Take a planar convex body, take a direction theta, and take a direction theta, and consider the length of the chord you see in the figure, which is obtained in this way. You move along theta, coming from the upper right, and enter in C by length delta, and measure the length of the chord. Of course, the length of the chord cannot be too small. Cannot be smaller than delta, essentially. Otherwise, we lose convexity. It's easy to make consider different examples. For example, in the case of a square, the length of the chord is either delta or say 1, in the case that theta is perpendicular to a side. In the case of a disk, the length of the chord is delta to the 1/2. And there is a relation between the Fourier transform, the characteristic function of C, and the length of the chord, which is due to Anatoly Podkoritov. It says, take a convex body and take the chords introduced before. Then the Fourier transform is smaller than the length of the chords times rho to the -1. Observe that we have to take two chords at opposite parts of the body. We have to take the direction theta and the direction minus theta. Podkoritov also proved the converse of this result, which is what we actually need. Suppose that the chords are larger, the length of the chords for a given theta in an interval are larger than delta to a certain power sigma. Then there exist positive constants such that the Fourier transform, the L2 norm of the Fourier transform of a dilation is larger than rho to the -1 minus sigma. Rho to the -1 is the -1, which appeared also in the upper bound. And observe that you need to have an average, because consider the case of a disk, for example. The Fourier transform has zeros, so you cannot bound it from below. But if you average on a given interval of dilation, you can have a sharp bound. An example with a sigma different from 1/2, take C symmetric and suppose that a part of the boundary coincides with the graph of the function y equal absolute value of x to the 1/sigma. Okay. The Ball-Lauer bound can be proved using second-order modular smoothness. Take an L2 function and define the first difference, phi of x plus x less phi of x. Take the second difference and take the modulus. It can be proved that this modulus smoothness is equivalent to the chord, to the length of the chords in the following sense. Take the largest value between the two direction you can enter in the body. This is stated for a function in one variable, but is equivalent to take a convex body and to take one direction. But anyway, in this form, take a function which is supported, non-negative and concave on the interval of length 2. And the length of the chord relates to is related to the Fourier transform. Then one can prove the following result. If we take the Fourier transform of the L2 function for large S is bounded by the modulus of rho to the -1. If we take the Fourier transform for small s, it is bounded by rho square times the modulus. And as a consequence, one obtains a lower bound for the average decay of the Fourier transform of S, for the decay of the Fourier transform of F. The last inequality comes from the following splitting. We turn the second difference via Parseval identity in e to the 2 pi I hs less 1 to the power 4, and then split into 3 parts. Then we have to show that the first and the third part are small enough by using suitable constant alpha and beta. The n to the 1/2 lower bound is a particular case of the following result. Suppose that we have a convex body where the chords have the lower bound delta to the 1/2 in a certain interval and delta to the sigma in another interval. Then this sigma plays the role and forces the discrepancy to be larger than n to the 2/2 sigma plus 3. For sigma equal 1/2, we get the previous result. This ratio, 2/2 sigma plus 3, takes all the value between 2/5 and 1/2. N to the 2/5 is a universal lower bound when we have a piecewise C2 boundary and we are not in the case of a polygon. which is what is stated in this proposition. Okay. Observe that if the boundary is C2, here is a pretty trivial observation which explain why positive curvature does not matter. If the boundary is C2, then we have the lower bound delta to the 1/2 for every theta. This can be proved by by splitting the boundary of the convex body, writing it at a graph of a convex function and integrating. In a sense, we need the lower bound for the chords. Suppose the boundary is very flat. Even the boundary contains a segment. The chords are large, but we need the lower bound. So if it is flat, the lower bound does not change. It can be larger, but we need to prove that it is larger than delta to the 1/2, which is always true, which is still true. Okay, we can have a slightly different point of view. We can consider the arc length parameterization of the boundary and replace the lower bound for the chords with this property, that gamma prime of S prime less gamma prime of S second is smaller than S1 S prime less n second to the power alpha. This is equivalent to a lower bound for the chord in the line A, in the statement of the theorem. Okay. If the boundary is not piecewise C2, if we don't find a C2 piece in the boundary, then we may have an unexpected behavior. There exists a planar convex body such that the chords are larger than delta to the sigma for every direction, but there is no interval where we have delta to the 1/2. This is a bit of a pathological construction, but it may happen. So the theorem can be stated, another theorem can be stated in the form. Suppose we have this lower bound for the chords. Then there exists a constant such that the square of the L2 norm of the discrepancy is larger than n to the 1 minus sigma. Again, the C2 boundary result is a corollary, amounts to the case sigma equal 1/2. The previous remark is just to say that the assumption of the theorem is not void in a sense, in general. The details of the proof depends on Montgomery's argument, which depends on the square we described before, where we took the terms of the sum of exponential. This square in Montgomery's argument has to be modified into a overposition of rectangles. A superposition of rectangles tailored on the convex body. And the length of the rectangle, the ratios of the sides depend on sigma, depends on the curvature of the body. And in this way, instead of working with a rectangle, we take a superposition of rectangle which stays below the average of the Fourier transform of the characteristic function. Then we have the lower bounds, and these lower bounds can be complemented by upper bounds like this one. Consider sigma between 0 and 1. Remember, sigma equal 1 gives you 2/5, which is the case of piecewise C2, and sigma 1/2 gives 1/2, which is the disk. Then we can give an explicit construction of a planar convex body where this upper bound holds true for an increase, a diverging sequence of nj. Remember, nj is the number of points. So we have to construct a convex body, and we have to construct to choose a sequence of sampling points. The convex body is essentially the one we have considered as examples up to now. So take absolute value of x to 1/sigma as the shape. The construction of the points in the finite set depends, is related to the following fact. First, we have to give estimates of the costs for this convex body. And this is not immediate, but is not strange. You have a body which is essentially a bit less shrink than a parabola. And then you have to compute the length of the chords. The result is this: the length of the chord has have these values up to constants. Then you have to choose the endpoints. In order to choose the endpoints, we take an anisotropic grid. So we take a grid of which is not where the fundamental set is not a square but is a rectangle, and that's enough. For every positive integer j, we take nj equal to the sum of the product of these two integer parts. Let k be the first term, L the second one, and we take the points UKL in this grid where in the abscissas the denominator is k, and in the vertical part the denominator is L. So we have rectangles in place of squares. Then we apply Parseval identity, and we are left with this sum. Observe that this sum is equal to KL when the terms are multiple of k and 0 otherwise. And then we have to evaluate this sum, and this has to deal with the with the ratio of the coordinates, so that the composition of the integer points into suitable angles, and the proof. And this is enough. Thank you very much for your patience.
So now is the time for questions. So if anyone has any, I have a couple. So, but anyone else before me?
I would like to ask a question. Thank you very much for the talk.
I have a... Who is speaking?
Alex here. Hi.
I don't see.
Well, regardless, I am the voice from the void, from outer space.
This is Alex Letuk.
Okay.
Hi, nice to meet you.
Now I see you.
So I have a maybe naive or slightly tangential question. So clearly these methods, the fact that we use these methods is related to the fact that we use L2 discrepancy to measure irregularity, right?
Yeah.
So for example, I imagine that if we shift to LP or something like this, applying a Fourier transform wouldn't be as pleasant. Is this correct? So that's the first part of the question, and the second part is maybe you're aware of results where local properties like separations can be characterized. Okay, so let's take a Kronecker sequence, right? Let's take a Kronecker sequence, and instead of looking at its discrepancy, we look at things like separation on torus. How does that depend on alpha? So results of this.
What does it mean?
Of this study.
What does it mean considering separation?
Well, so presumably different alphas, right? So if you vary alpha in the Kronecker sequence, you will get different best the smallest distance between elements in this sequence.
Okay.
Right. So you take torus, you draw the sequence, and presumably the separation. So if you throw in, if you take the first 1000 n terms from the sequence, there is dependence of separation of the smallest distance between 2 points on alpha.
Okay.
So can you study something like this? Or are you aware of results
on the
of this
separation? I have no idea. I never knew this type of problem. On the L2, there are results on LP. There are some results which you can prove for P larger than L2. Particularly, of course, I'm talking about upper bounds. You can construct upper bounds. For example, you can take L4, or you can take powers of 2, and or there are more general approaches, but of course it is much more painful than dealing with L2 norms.
I see. I see. Thank you.
Anyone else for questions?
I was curious about something. So for the results that you had where the boundary needed to be C2, maybe you said this and I missed it, in which case I'm sorry. If the boundary is more smooth than just C2, is there anything you gain from that?
No, I believe you don't get anything.
Okay, thanks.
Because consider the case of C2 with the boundary containing a segment, which is what in many other problems we should try to avoid. But if the boundary contains a segment, you get exactly the same result.
Okay. Thank you.
It's because if the boundary contains a segment, the costs are larger.
Oh.
But now you work with lower bounds for the chords.
Right.
Alex again.
Okay, yeah, sorry. Can I ask a follow-up since we started talking about chords? So would your methods apply if we allowed rotations?
If we allow?
Rotations.
Okay, this is for a given direction. Of course, you can take an average of the chords over rotation.
Mm-hmm. Okay.
So actually, this argument was born in the context of rotations,
Mm-hmm.
because
Yeah, exactly.
when Anatoly Podkoritov used this argument, he was interested in proving results on the average decay of the Fourier transform, where average means average over rotations. So actually, this topic, this argument start inside the rotation, but basically it's not necessarily linked to rotation.
I just thought it was interesting that the way your results are stated are just for dilations and translations, but it seemed that, I mean, looking at chords, sort of, you can include any rotation you like, right? So
Okay.
it seems natural.
If you add rotation in the L2 average, you get the same result you get for the disk. Actually, the result of Montgomery and Beck was stated in this form: take a convex body and rotate it. But since here we were interested only in dilation and translation, I took the example of the disk to avoid confusion, to reduce confusion.
Thank you.
Observe that the argument of the chords does not work in more than two variables.
So I have a couple questions. As mentioned, the curvature didn't end up playing a role, but I'm just wondering what were some of the sort of heuristic reasons why you expected it might play a role?
Because in Fourier analysis, it's quite common to see a specific role for positive curvature. Just a matter of tradition.
Mm-hmm. Okay. And then, so these sort of intermediate results, you have something about the convex set behaving like a disk on some interval of rotations, right? But I'm wondering if you've considered other types of sets of positive Lebesgue measure. So if you have the Fourier decay sort of matching that of a disk on a set that's not an interval of rotations. Have you considered that case? And
you mean like lacunary directions also?
Yeah, for some Cantor set.
No, I know this topic, but I don't see a link with what you have done here.
Mm-hmm.
Actually, I hope to attend a talk of yours on this topic.
Thanks.
So yeah, I guess just as a follow-up question. So this is what we're trying to look at with Michelle. So if you're, say you take the squares or rectangles, right? If you allow all rotations, you're going to get the exact same thing as for the disks, right? So now assume you allow rotations only in some directions. Okay, and in particular, if you allow rotations in a interval of directions, then essentially your argument goes through and you get 1/5. Well, 2/5 with square, right? So, right, the question is, it's not clear whether that 2/5 is sharp in this case, because you cannot just create a convex body like in your case, because now this is given. You have and it may be possible that you would still get into the 1/4. So here, do you have an intuition what would happen if you take rectangles and allow them to rotate just in the just in an interval?
I don't have a feeling in this sense. The way I see it, but you can tell me whether it's correct or not, is that I imagine, for example, a square.
Mm-hmm.
And I take a sort of a singular direction,
Mm-hmm.
which gives a certain behavior.
Right.
Okay? Now, instead of taking a whole interval, moving away from this direction, I take something lacunary as a sort to move, but not too much from the singular direction. That's the way I imagine what you are doing. I don't know whether it is your point. If you see lacunarity as a way to move not too much for a singular or a regular direction, in a sense.
That's one way to view it, but there is a much simpler question. So assume if we average, take the square, right? And now start rotating. So you have a singular direction, but start rotating it, but don't take all the rotations. Take some rotations from minus epsilon to epsilon, from minus pi over 10 to pi over 10. Okay. So you smooth it out a little bit, but still you're not taking so you still have some directions which are not as good. So you don't smooth it out completely over the whole set of directions. And in this case, you can, so for this interval of rotations, your argument essentially goes through, but we do not know whether it's sharp or not. So that's one question that arises here. I suspect that it may be possible that for this setup, when you take square with even a small interval of rotations, that it may still be that you would get n to the 1/2, even though you don't have this curvature, the C2 type situation on the whole set of rotations. But I'm not 100% sure.
So
it turned out to be much trickier.
Mm-hmm. So your point is not to stay close to a sort of singular direction, but to use less rotation as possible.
You're right. So I'm using rotations, but I'm not using all rotations. So I'm taking a square, but I don't rotate it in all possible directions. I just rotate it in some directions, say from minus epsilon to epsilon, from some fixed interval of rotations. So this setup, in a sense, is very similar to your setup, because you have an interval in which you have some decay of the. So instead of having a curvature or some analog of curvature of the boundary of your set, you have rotations.
I see.
So in your case, you had some decay on an interval. And in this case, instead of that, on an interval, we have rotations. So on that interval, it's the analog of having C2 on an interval.
But this can be handled only in the case of lacunary direction, which assume angle 2 to the minus n.
No. We take all possible, so fix a square and you take translations, dilations of the square and rotations, but rotations only by angles between, say, negative pi over 10 and pi over 10, or any constant that you like, but not all possible rotations.
So a whole angle.
Yeah, a whole angle, yes.
So there is no lacunarity.
No lacunarity. No. There's no lacunarity. You take all possible rotations of the square, but in a small interval.
Okay.
Not from 0 to 2 pi, but in a small interval. And the question is, what would happen with discrepancy in this case? Of course, once you answer this, you can then answer other questions about lacunary directions, about Cantor directions. But I thought that it would be very simple for the interval, and it doesn't seem to be very simple. So what I'm saying is that your argument that you just presented, it works for the case of the interval, because it's a very similar setup.
Yeah. Because apparently one can say that rotation does not enter in Parseval. So you have a integration of a given angle and this angle remains. So you have this angle which moves to the Fourier transform side.
Oh, right, but you would have an estimate on the decay on the Fourier transform only on this angle,
Yes.
only on this sector. So that's the problem. That's why you cannot use it everywhere. So you wouldn't have the full estimate then. So yeah, it turns out to be trickier than I initially thought about it. I thought it would be more or less straightforward, but it's not.
If you have something, please send us.
Okay, yeah. Well, as I said, as Michelle mentioned, yeah, your argument goes through completely for this setting. So so you do get n to the 1/5 this way, or 2/5, because you sort of have C2 on an interval of rotations, and you have well, essentially you have this delta to the first power estimate on the other part where you don't take rotation. But yeah, but I don't know if you can improve that for this setting.
Right.
Yeah, once
and
we type something up.
Because an interval obviously contains the Diophantine properties may suggest that the true discrepancy would be or n to the 1/2 or n to the 1/4.
Yeah.
Just
No,
because
I don't understand. What Diophantine properties you refer to?
just because in other situations where you're restricting in the case of rotated rectangles where you're restricting the rotations, Dima has a paper from a few years ago where they do study like lacunary sequences and other types of sequences, and in that paper, Diophantine properties really come into play. The Diophantine properties of the allowed set of rotations, I mean. So if you're allowing an interval of rotations that kind of contains a number of every type, and so maybe you would expect that it would match the lower bound for all rotations. But so far, due to your arguments that go through in this case, we at least have n to the 1/5 for a restricted interval, but unclear whether it's n to the 1/5 or n to the 1/4.
I see.
Anyway, yeah, so if we want to stay on a little bit longer, just chat a little more.